Welcome to another week of Physics 106, Physics Lab, Principles of Physics 2 Lab. This week we're going to be talking about electric fields and electric potential. Unfortunately, electric fields are a pretty abstract concept and it's difficult to find a good quality hands-on lab. So both labs this week are going to use simulations, but since it's our way to have two halves, the first half is going to be this simulation, the second half will be quote unquote the virtual one, which you'll be doing separately. So we're going to be using the charges and fields simulation from PhET for this particular lab. We'll load it up. And we're going to be talking about electric fields and electric potential. We'll get into some definitions a little bit later, but the first 4 questions ask you just to look at the simulation. What are the things you can change in the simulation? What does the E field sensor show? Well, that's kind of obvious, but we'll show it to you in a second. And select show E field. How does the color of the arrows relate to the strength of the field? And finally, if one charged particle has a charge of Q, how can we make one that has plus 2Q or minus 3Q? Oh man, okay. So let's go back and say, what can we change in the simulation? Well, I can add charges. Put them in different places. I can move them around. I can take them away. I can add sensors. Here's your E field sensor. What does the E field sensor show? It's showing 2 things. It's showing the magnitude. Notice the arrow gets longer as the field gets stronger and shorter as the field gets weaker. It shows the magnitude and the direction of the electric field. So we can add charges and electric field sensors. We can show the electric field, we can show the strength or just the direction of the electric field. We can show the voltage, which is represented by shaded colors. If we add another one in here, you can see that the more shaded it is, the stronger the potential, and as that shading fades out to black, the potential gets weaker. We probably have talked about it in lecture, but the potential is 0 infinitely far away and gets bigger as you get closer to the charge. We can look at specific values of things. So let's look at that. It shows not just the direction and magnitude, but now the sensor shows numerical values for it. Showing numerical values for the angle and for the strength of the field. The units for field here are different than the units that we use in class, but they're still base units, so the units are equivalent. And you can also get a grid so you know you're putting the stuff where you want to put it. That's going to be useful for us. That way we know they're in line if they're supposed to be in line. We can get the angles exactly how we want them. Okay, so we answered 2 things so far, right? What can we change about the simulation? What does the sensor show? Select show E field. What does the color of the arrow represent? Oh, I kind of gave that one away, didn't I? Well, remember the E field is strongest as you get closer to the charge, and these are brighter. They're more clear. They kind of fade out as you get farther away. See the arrow out here is much dimmer. It's much more translucent. And lastly, what if I wanted, instead of, so right now 1Q equals 1 nanocoulomb. So we have plus 1 nanocoulomb or minus 1 nanocoulomb. What if I wanted a point charge here that was more than that? Well, think back to our principle of superposition. If I have 2 charges here, the electric field strength is going to add vectorially. So since both of them are producing an E field in the same direction, radially out from them, the E field's going to add up, like vectors. So now, since there are 2 charges there in the pile, the E field produced is going, the charge there is going to be 2Q, and the E field is going to be produced as if that was a point charge with a charge of 2Q. If I've got a negative, that's -1. Well, there, now it's -2, and now it's -3. All right, awesome. That's our first 4 questions. That wasn't too bad. Next, some information about electric fields and electric field lines. A couple key points. The field lines emanate out from the positive. They emanate into the negative. They go radially out, so they go straight out from the center of the charges if it's a single point charge. And they stretch off into infinity. They don't begin or end except at charges. So they radiate out from a positive charge and into a negative charge. That's the only places they terminate. And they don't cross. Because they're adding as vectors, they don't ever cross. It wouldn't make any sense. Right here in this box is definitions. We've covered this in class. I'm not going to cover it right now. You can read those on your own. And it gives the equations. Again, we covered those equations in class. This equation right here, F equals Q times E, it's really actually very similar to the force of gravity equals M times G, where G is the gravitational field strength and M is the scalar quantity multiplied by that field strength. So you have seen stuff like this before. It's not new. This equation is derived from Coulomb's law. Okay, now, fields around an isolated point charge. We want a point charge with a value of 4Q. All right, so let's put the grid up there so we know where we're putting them. And there's a charge due to 1Q. If I was drawing this, I would draw field lines emanating out. And the closer together the field lines are, the stronger the field. Let's go back and look at that picture. Where are the field lines the closest together? Well, if I made a circle here, I can get 2, maybe 3 lines in that circle. If I made the same size circle out here, I can at most get 1. There's even spots where I don't get any. So obviously the field line density is bigger nearer to the charge. Field line density, or how many lines there are close together in a given amount of space, represents the strength of the field. So if I was drawing this with field lines, I would just draw field lines around it. But if I double up the amount of charge, well, the field got stronger. Notice that these got sort of brighter when I put them in there. And the ones out here that were kind of dim before, they became brighter too. So the field's getting stronger, which means when I'm drawing it, when I'm sketching it in my notebook, I'm going to draw more field lines coming out. The stronger it is, the stronger the field is, the more field lines I'm going to draw. The number of field lines represents the strength of the field. So add another, and we have 4Q. You hear the puppy playing with his ball upstairs. Now, if I was sketching this, like I said, I would initially draw a few field lines coming out. When I go from 1Q to 2Q, I'm going to have twice as many field lines. When I go from 2Q to 3Q, I'm going to have more field lines. 4 is going to have 4 times as many field lines as if I only had 1. All right, awesome. Next, a point charge with negative 2Q. Okay, so negative 2 nanocoulombs. Oh, I turned the grid off. Guess we don't have to have the grid on this. Put them in the middle there. So it's not going to be as strong. The field is weaker. It's half as many field lines as I had before. That being said, there's one other thing that's different. Before, the field lines are pointing out because it was a positive charge. They emanate out from the positive charge, and now it's a negative charge. So they're going in. They're pointing in towards the negative charge. So there's going to be less field lines. Now, twice as many as if I only had 1. Like it's twice as strong when I add another charge into the pile. But it's half as strong as when there are 4. There was 4 positives, and it's pointed in instead of out. Okay, onward. Draw the field lines for the scenario below. Make sure you're sketching continuous field lines. So we're not drawing those arrows as darker or lighter like in the simulation. We're going to draw them like this diagram here, continuous field lines. 2 unequal, unlike point charges. We're creating a dipole. We have 2 different poles. We'll have maybe one is here. Let's put them in line. So put them on the grid and make sure they're in line with each other. So we'll have one right there, and they're unequal, so we'll have another one over here that's maybe twice as big. So right now it's pretty symmetrical. We have field lines coming out of the positive and into the negative, out of the positive into the negative, and they're looping around regardless of where I go out. They always loop around and come from the positive to the negative, and like I said, it's pretty much symmetrical. But when I add, let's say I add more negative charges, it doesn't say how they're unequal, it just says that they are unequal. Now it's stronger over here. It's weaker over here. So the field lines come out and they get pulled really hard over to the negative. They come out and they get pulled really hard over here to the negative. Here in the middle, it's just going to be straight across, obviously. But out here, it's getting pulled, and it's sort of teardrop shaped towards the stronger charge. If I did it with the positives, it would look a little different. I can get my plus, I can get my minus, and if I add more charges to the plus, so now it's coming kind of straight out and pulled in. It's stronger, and a good way to check this actually is with the sensor. So if I put the sensor here, it's going to point in the direction of the field lines, and as I move the sensor in that direction, it's getting weaker, and it kind of pulls around. I just follow the arrow, and that's going to be the arrow that I draw on my paper. So that's one way you can do it, or you can just visualize it, sketching like this. Awesome. And the last box here, 2 equal positive charges. Okay, so we're going to have a charge like somewhere in here, and then on the same line, charge over here. So they're both emanating out. There's nowhere for them to terminate, so there's no like negative charge in this diagram. That said, they're just going to continue off into infinity and get weaker and more spread out. On this side, it doesn't really change much, as if it's like a single point charge. So out here, it's pretty much the same. And out here as well. Since they're equal charges, it's going to be symmetrical. Symmetry is our friend. Where it gets really interesting is in between them. So the field comes out here, but there's also a field due to this one, and they add up as vectors. Remember, electric fields are vectors. So the field strength at this point is going to be the field strength due to this one, and the field strength due to that one. So as it gets closer to this one and farther from the one on the left, it's going to feel more of the effects of the one on the right. So it's going to come out and then bow up towards the top. Same with this one. It's going to come out and then curve up towards the top. Down here, it's going to curve out and go down towards the bottom. Right here, dead center in the middle, if I put my sensor there, right exactly in the middle, there's no arrow. Does that mean there's no field? Yes, exactly, no field, because the field from this one is pointing to the right, the field from that one is pointing to the left. They're equal in magnitude and opposite in direction, which means the vector adds up to 0. If I move it a little bit to this side, it feels a field. If I move it a little to that side, it feels a field. But right dead center in the middle, if I can get it back right in the middle, not going to feel any field at all. There it is, right in the middle. So again, when I'm close, it feels the effect of this one the most, but it comes out and it curves down. If I go up here, it's going to come out, it's going to curve up. Alright, so far so good. When you have 2 like charges in a line, like we just had, where is the electric field the greatest? Is there ever a point where the field can be 0? We literally just talked about that. When you have 2 unlike charges in a line, where is the field the greatest? Is there ever a point when the field is 0? That one might be a little bit more tricky, but I think you can handle it. More complicated scenarios. 3-point charges equal like charges. Okay, so 3 equal like charges. 3 positives, 3 negatives, all the same amount of charge. You can make that look however you like. When I did mine, I had 3 positive charges sort of in a triangle shape. So I had one up here somewhere. Yeah, I'm going to put them in the grid. I like having the grid. It lets me place them a little more carefully. I had one kind of down here and one somewhere over here. Makes a fairly complicated pattern. Now, if you're stuck on how to draw these and you're like, this doesn't make any sense, the arrows are going all over the place, I don't know how to do them continually, you can do the sensor trick like I told you and follow the sensor and see what it says as you're sketching these. There are also some diagrams of these online you can find. Next, 4 charges, 2 positive, 2 negative, all unequal. Alright, so on my grid. Let's look at that one more time. 4 charges, 2 positive, 2 negative, all unequal, all different sized charges. Yours might look different than mine. I put mine in a square, and I had 1 charge, 2 charge, red charge, blue charge. They are red and blue. That's funny. But then I had 3. We want these as close to right on top of each other as we can. I'm leaving mine a little offset just so you can see them in the video. And then 4. Again, you don't need to clump them. You can put them right directly on top of each other. And again, this is fairly complicated, but it's not impossible, and I think you can handle it. Yours doesn't have to be in a square like mine. I think the square is the easiest one to draw, though. Now, before I go too far, I guess I took that out. In my copy of this lab, I guess I edited that out, but in my copy of the lab it says place field sensors around and draw them in, just to show what the field is doing at various points. You don't have to do that because it's not in your lab, but you can if it helps you. And then the last scenario, 5-point charges, all unequal, 3 positive, 2 negative. All unequal. Okay. So, you know what? I'm going to take what I've got and just add one more. I'm going to put one right in the middle. Let's make it positive. And we'll give this one a charge of 5. 1, 2, 3, 4, 5. The point of this exercise, it makes you think about how these fields are going to add up as vectors and how you can draw these lines continually following the rules that we laid out in section 1. So like there's field lines that are going to go from this positive, big positive to that negative. They're going to come through. Now that one is smaller than this one, so there's going to be more field lines coming into this one. There's going to be less field lines coming out of that one, but they're still coming out. This is going to be producing the strongest impact of the field because it's got the biggest amount of charge. So all of that is stuff that you'll think about when you create yours. All right, the field around charge distributions. Oh man, this is kind of a fun one. Make a line of 10 positive charges by placing them close together on a horizontal row. Sketch a diagram of the field lines produced by that. How does the field change as you move along the line? You'll use the sensor. Then construct a parallel plate capacitor by adding a second horizontal line, equal in size and opposite in charge, below the positive charges. Okay, so we're going to need the grid. And let's put them, all 10 of them, across this space. Four, 5, 6, 7. That's a little off the line, but not too bad. 8. 9, 10. There's my positive line. In the 206 class, they have some more complex charge distributions than just a line of charge, but this can be complicated. If you get into the math of this, it requires a little bit of calculus integration. So what does the field look like? Well, it's really strong when we're right next to it, and it points away from the line. Here in the middle, it's pointing straight down. But over here, there are more charges over here on the right than there are on the left, so it's going to be slightly angled to my left. As I get farther and farther, it's angled more and more and more. As I get farther away, I guess you can't see it, the line's getting... Let's do values, then you can actually get an idea. So as we get farther away, yes, it does get weaker as it gets farther away, and stronger as you get closer. All right, sweet. Now let's make another plate right down here. It doesn't say where, but we're going to put them far enough apart that I can see what's happening in the middle, but close enough that they're still interacting strongly. That's 4, 5, 6, 7, 8, 9, 10. Well, I made this one a little bit more condensed than I made that one, but I think it will do. So look at this. In between the plates, it's almost straight up and down. The variation, the slight variation in angle that we're seeing, it's only going between like 93 and 89. So it's almost, the average here is 90 degrees, meaning it's going straight down most of the time. And the variation is because I'm using a touchpad here and I'm not getting them equally spaced throughout. So it's the field density, the charge density isn't equally distributed on the plates. And the plates aren't the same length. But we see that in between the plates, the field is pretty much uniform in direction. It's pretty much straight up and down, especially right in the middle. And here in the middle, the field strength is fairly uniform. It gets weaker as it goes to the edge, but in the middle it's pretty much uniform. This is called a capacitor, and we're going to be doing labs and learning a lot about capacitors. A parallel plate capacitor, to be specific. So yes, the field lines are going to be parallel going between them for the most part. They get more complicated as we go out here. With capacitors, we really care about the space in between them, though. Okay. Awesome. That's the first half of the lab. Or the first 33% maybe? I don't know. There's 3 sections, but I think that was a fairly large section. Onward. Potential, potential energy, and equipotential lines. Okay. So potential is something we talk about quite a bit. That's when we talk about 120 volts when we plug something in, or a 12-volt battery, 9-volt batteries. The voltage, that's electric potential that we're talking about. Specifically, the potential difference between the 2 terminals of the battery. If we haven't yet, we're going to be talking about that in the lecture. I want you to read this. It gives more detail than I'm going to give. But think about a topographic map. If you've ever seen a topographic map, it shows lines that show stuff that is at the same elevation, or gravitational potential, if you want to call it that. When we have spots surrounding a charge that are at the same level of electric potential, those spots are called equipotentials, and we can draw lines that connect all the equipotential points and create equipotential lines. Okay. We're going to talk about that in class 2, so read up on that. All the information you need is all right in here. Okay. As with topographical lines, that's what I just said. A series of equipotentials are drawn, so the difference in the values in the neighboring lines is the same. Got it. Is more work, less work, or the same work needed to move a positive test charge from infinity to an equipotential contour that is 1 meter from a charge, or 2 meters. Sorry. I wrote read 1 and 2, but it's 0.1 and 0.2. It's still twice as far away. Well, it takes more work. Imagine this. So I'm going to clear this up. I have a charge. I have a positive test charge. This sensor is going to be my positive test charge. At infinity, infinitely far away, there is no field. There's no potential. When I bring it close to the charge, the field gets bigger and bigger and bigger and bigger and bigger. And it's harder and harder and harder for me to move that charge. It takes more and more and more force because there's more force, Coulomb force, pushing away. So it's easier to bring it to a distance farther away than it is to bring it to a distance that's closer. So it takes more work to bring it to 0.1 meters. How much work is needed to move a charge from one position to another position that is at the same equipotential? This lab uses equipotential contours. I don't use that terminology. I just call them equipotential lines. It means the exact same thing. Well, if it's at an equipotential, it's at the same potential. Equa meaning equal, potential meaning potential. If it's at an equipotential line, the energy hasn't changed, and therefore no work is done. No change in energy, no work. Sketch electric field lines and at least 3 equipotential contours for a single isolated negative charge. Well, this is a single isolated positive charge. If that's what that looks like, what's the difference between that and a negative? Well, the field lines will be pointing the other direction. If we have a single negative charge, it's going to look exactly like this, but with the field lines pointed in. And since it is symmetrical, the field lines are all pointed in, the field line density are going to be concentric circles, right? The equipotentials are going to be concentric circles just like this. Something it says in the text here, the equipotential lines are always perpendicular to the field lines. That's good to know. They do get more complicated when we don't have isolated point charges, but for an isolated point charge, because they're circles, symmetry is on our side, and we can just sketch it the same way. All right, we're making progress. Okay, open the charges and fields FETSIM. We have that open already. There's the link to the thing we already have open. Drag 3 E-field sensors to the corners of grid squares around a positive test charge. Okay, so we've got our positive test charge. Let's put it right here so that we can make a square. We'll make one corner of the square 2 up, 2 over, and 2 to the right. All right, it's not, man, I'm not getting exactly on that line, but close. All right, so far so good. Calculate the electric field strength at each sensor from the vector equation. Okay, so this is 1 meter. This is 1 nanocoulomb. The electric field strength here is going to be K times Q, 1 nanocoulomb, over the distance between them squared. This one's going to be a little bit more complicated. You got to use Pythagorean theorem, 1 meter by 1 meter. If you don't believe me, let's check. Make sure that it's 1 meter. Yeah, 100 centimeters. And you can calculate that one. I'm not gonna give you that one. Of course, you can do it yourself if you open up the sim. Once you've calculated those and shown your calculations, here, put your answers in. Then turn on show numbers and compare what you got. So show the numbers, and it actually shows you. Remember, I don't want you to get confused because of units. I really am, units are important. We don't want to mess them up. But, oh geez, oops. I bumped the button. Okay, units are important, but volts per meter is SI, so it's going to be the same as what we normally use. No worries on that front. Okay, so plug in your calculated values that you got, the measured values you just got off of the simulation, and then calculate your percent difference. Turn on show E-field option. I guess that's already on there. Good. Yep, talking about stuff we already know. Compare this FET diagram to figure 2. Figure 2, figure 2, figure 2. Right there. Turn off the E-field. Look at the values by the sensors. So turning that off so it's not distracting us, and we see this one is 9.2, that one's 8.6. We would expect these to be equal. My guess is that I'm not exactly where I need to be on my, like they aren't exactly on the grid lines the way where they're supposed to be. This one's farther away, so we expect it to be smaller. Now, since those are the same distance away, they should be about the same, they should be exactly the same. We would expect them to be the same amount of electric field at that point, and therefore the same amount of electric potential. There's a tool on here that lets us do that. So it's saying place a line of sensors that enclose the charge, creating an equipotential surface. And then we're going to sketch it when we're done. So we're going to try to get a bunch of them that are at or about 9. Well, that was pretty good. That makes a pretty nice round circular shape. We have an equipotential surface. If I pull my voltmeter, which one of the upcoming questions is going to ask you to do, and I put it right on one of those sensors, and I click the pencil, it makes an equipotential line. Check that out. That green line, and it follows my sensors that I put on there, all at 9. Sweet. Here it is. That's what it's telling you to do. It's saying using the voltmeter, add 5 to 10 more, just to see what they look like. I think you know what they're going to look like, but let's do it. There's one. There's one. Normally they're equally spaced so that they are the same difference in potential in between all the different equipotential lines. How many is that? 4? Add a couple more. Let's have one way out here. Notice the potential is getting smaller as you get farther away. It approaches 0 as you approach infinity. Oh, so what's going to happen if we replace that with a negative charge? Do not click clear all, just drag a negative charge in the same place as the positive. Put a negative charge there. I put it right in the middle. Look at that. That's not exactly right in the middle, but that's as good as I'm going to get it. And they're all pretty close to 9. These ones, it looks like I'm a little bit above the line. That's a little better. So they're all pointed in, and the equipotential lines, well, the equipotential lines don't change. You guys can do that on your own if you'd like. All right, the last part, I think. Yeah, last part. This one's pretty short. Creating a dipole. Based on earlier sketch with predicted E-field map for a dipole. We made a dipole earlier, so you're just going to make one that's very similar. We got a positive and a negative. Get my grid on there. There you go. Yeah, so we got it. We have a positive charge and a negative charge 2 meters away to the right. Positive charge, 1 meter, 2 meters, right there. Calculate the electric field at the midpoint between the two charges. Remember, E equals KQ over R squared. The distance here is going to be 1 meter from each one. Since it's a vector, we're going to add the electric field due to this one to the electric field due to that one. They're in one line, they're in the same direction, so they're just going to add up as vectors. Compare the measured to the calculated. So click on values, you'll get your measured value. Compare that to what you calculated. Using the field lines shown, predict the equipotential contours and draw the sketch. All right, do that first. Don't mess around. It says in your lab notebook, just do it right here. Like right here. Or in your lab notebook and share a picture. That's fine too. I don't care. And now let's make some equipotential contours. Put one right here. And we'll put one right here. How about one right there? How about one just on the other side? How about one like here? This is so cool. I love this feature. Is that what you predicted? What if we put one up here? Sweet. If that's what you predicted, great. If not, that's okay too. Sketch this as well. If your prediction does not match, why is it different? What was different than you expected? This is cool. I think we actually do this in class, so probably I've shown this to you so you can read it yourself. And there are a couple summary questions for you to answer. Just adding up some vectors to calculate the electric potential at a given point. That's it, folks. Have a great day.